I'll give an introduction, then we can get started. Okay.
It's a good place to start is the guide page, pdemodels.nb.
Okay.
And because it's easy to click from there.
Join
the source.
This live stream. We are talking about physicalizing our PDE system, in a sense. I mean, so assuming I want the diffusion equation, for example, right? How do I get that?
Well, if it's non-physics, you can go down to use just a generic model to get a diffusion equation.
What's the what is this?
It says generic down there?
No, I understand. What's the guide page called?
PDE models.
Oh, sorry.
Yeah. Do I have this, or does it just get updated today?
No, it's been there forever. In the source. There it is.
Okay. Where's generics here? I mean, so. I mean, I'm not hugely enthusiastic about, the immediate physicalization of these things. I mean, some of them, like diffusion term, convection term, that makes sense to me. Okay, do we have units in all these things? Like when we're doing heat transfer, do we have units there?
Yeah.
All right, well, where do I start? Where should I start? Should I start with the diffusion equation?
I think you should start with the things that acoustic, heat transfer, mass transport. And start with the differential model and then go from there. Yeah.
So the first argument is the variables. Is that correct?
Yes.
I mean, it doesn't say that. Okay, variables, parameters. Okay.
Okay, but it's a generalized notion of variables. It's dependent and independent.
I understand that. That list. So how do I know what variables I have to specify for this model? How do I know what variables I have to specify for this model?
So it's always the same. It's always the dependent variable. Then you have either a time-dependent or a non-time dependent version, and then the independent variables.
As a list.
As a list.
So there's an assumption that there's a single independent variable. Is that correct?
In this form, yes. There's other forms where you have a list of dependent variables.
So what about the wave equation, for example?
That's a single equation. So it's just any dependent variable as you like to name it.
No, but I understand. But the wave equation has time and it has space. Which one is a dependent variable? Which one is an independent variable?
So the dependent variable is the variable. I mean, t and x are both independent variables.
Okay, so here they're both independent variables, or not?
Yes. So
why are they listed? I don't understand. Why is the x in braces?
So you might have a two-dimensional acoustic.
I am well aware of that, but I don't think that's a good enough.
Well, Stephen, I think that the thing is we distinguish between time and spatial variables in our PDE solutions. So if you look at that frequency domain acoustic model, that's a purely spatial model, but it's using this frequency domain modeling system.
All right, so let's be clear what our meta model of physics is here. Okay, is it the case that you are assuming time is a single variable, and then you have some number of dimensions of space? Is that correct? So no. Time and space.
Or in this case, it could be frequency equivalently to time.
Okay. It could be wave number, presumably equivalently to space too, or
Right.
not.
Not in acoustics, but maybe there could be. But that we haven't seen that convention used.
Where's Laplace's equation? Is there a Laplace equation here? Where is Laplace's equation?
It's
Where's the
not.
Helmholtz equation?
So, I mean, we can, so Laplace
We need
equation.
those. We need those. That we need Laplace Helmholtz wave equation. We need the obvious named equations.
Classical PDEs, you mean? Yeah.
Yes.
Good. Yeah.
Yes,
Okay.
we need them.
They're,
Just like we need
a
triangles
little
when we're
further
dealing
down, they're
with polygons.
featurized, but we can make them. Yeah.
Yeah, we need them. We need them. Before we announce something with acoustics, we need the frigging Laplace equation.
The diffusion term is a generalization of the Laplace.
I'm well aware. I don't care. Just like a polygon is a generalization of a triangle, but we can't, there are many more people who understand triangles than understand, 17-sided polygons.
I'll add
Similarly here, Laplace equation is a well-known PDE understood by many people who do not go in for, yes, the Laplace equation is a diffusion term equal to 0, right? It's really important that we do this and not, okay, so the PDEs that have classic names need to have functions here. So are there any in addition to diffusion, Helmholtz, wave equation? I mean, clearly there are nonlinear ones like sine Gordon and all these kinds of things. But I think those are probably not what we can deal with because we're dealing here with, am I correct? We're basically dealing with linear PDEs. Is that true?
No, that's not true. We can do nonlinear PDEs, but the model form of the equation is given. And that's what says the model partial differential equation has the following form. That's the form we're constrained.
Okay, where's fluid mechanics?
We haven't covered. There are lots of domains we haven't covered. Fluid dynamics is one.
Okay. Okay. So the Euler equations, for example, we don't have those.
No.
Could we have those? I mean, are they the same?
Not with the finite element method.
Okay. Okay, but we sure can have Laplace and Helmholtz and things.
Yes.
Which are like, they should be the beginning of this before we get to any of these other things at the top.
Yeah, I mean, I guess a terminology question is, do we want to, so most of these models and terms are set up as things which we build up equations with. So do we want something that's just called Laplace equation and it just gives you the Laplace equation?
That's what I would think.
Fine.
I mean,
so the downside, the way that we do boundary conditions with finite elements is that you can't do that.
Okay, I need to understand that. I don't understand that yet. So let's loop back to that when I've understood that from this other stuff. Okay.
Yeah.
Okay. So okay. There are no parameters here, even though it's meaningless to have unit coefficients in this acoustic equation, is it not?
There are lots of parameters.
No, I understand. But here, with the default with no parameters, there are no, if I were doing this, it's a pity we can't do this with a, let's do it with a heat transfer model because I'm a little bit more familiar with what that should be. Oh boy. I really don't think it's a good idea to use capital letter variable names here. I don't know what the right thing to do is, but I don't think that's it. Use theta for temperature. It's another pretty common thing to use. Does that make sense?
Yep.
Okay, I don't understand this. I don't understand what this is. This isn't a model. This is the left-hand side of an equation, presumably. In what sense is that a model? Do you understand what I'm asking? What is this thing? This is the thing which is going to be set equal to 0, correct? Actually, that doesn't seem right. That's just a well, go ahead. What is this thing that you call a model? Do you understand my question?
Yeah, I mean, are you asking me? So
yes, I'm asking you. I mean, I'm asking somebody here. I don't know who is responsible for this, but whoever's responsible for this, I'm asking you what this
yeah.
is.
Okay, so the idea behind this modeling language is that we provide building blocks of model components.
I understand, but what is that object?
That object returns a part of the equation that can be used.
Okay, that's not called a heat transfer model. What is the definition of this object? In other words, if you were documenting that object there, that is not defining a model.
It's sort of an operator.
Okay, then that's what we should call it. It's not a model.
Yeah. Go back up in the notes. Okay, stop. Okay. There it is. Okay, that's what it is in its full generality.
But a model would be equal to 0. Is this thing equal to 0?
I mean, it will only become a full model if you actually specify the boundary conditions to.
Okay, then it isn't a model. Then what this is I don't know what the right term for it is, but it isn't model.
Well, but Stephen, the thing is that thing without the boundary conditions is equal to 0.
I don't care. I'm just saying you shouldn't call it a model. It's not a model. I mean,
I mean, sure, we can change it to some other name.
Yeah, well, that's what I'm talking about. That's what these reviews are about, is trying to figure out how to make it so people can actually understand what we have. And so we actually have the elementary stuff as well as the super advanced stuff. Now, let's look at the actual form you've got here. This thing here, oh boy, it's an inactive div. Wow, that's exotic. And what's this weird thing here? What's that?
So that's the coefficient. It's -1 is the default value.
And why is it in 2 levels of braces?
Because it's dot multiplied with the gradient, with an active gradient.
In general, Stephen, the diffusion coefficient is a matrix. So in one independent variable, yes.
It's in one dimension where it's a diffusion coefficient, the diffusion constant of 1. Somehow that's the default in this model, that the diffusion constant is 1 with no units. Is that correct?
Yes.
And that div is specifying its variable there, which is okay. And actually, I mean, that's a gradient, right? Oh yeah, it says inactive grad.
Yes, that's an active gradient.
And that's an ordinary dot there.
Yes.
Okay. So, okay, so where do I start seeing this thing be solved?
In the scope section, presumably, you'll find examples.
But I mean, obviously, you should show the thing getting solved in the basic. Oh my gosh. Okay. So, all right. So this is the beginning of the boundary condition specification. Is that right?
I don't see where you...
This here.
Yes.
That's the boundary condition, right?
Yes, correct.
Okay, so how about explaining, okay, so what's the general form of boundary conditions?
So the general form is that you first have the location where the boundary condition is, then the vars and parameters as specified for the differential equation operator model, however you want to call it, and then a specialization of what this specific boundary condition is supposed to do.
What do you mean by do?
I mean, if you want a boundary condition, you need to tell the boundary condition what value it should have at that specific location.
How does it know its surface temperature? What other things could I specify other than surface temperature there?
For the heat temperature condition, you couldn't specify anything else, but there's other boundary conditions that have other
So mathematically, what we're specifying, I mean, you know, it's Dirichlet conditions, it's Neumann conditions, things like that.
So everything that ends in condition will result in a Dirichlet condition, and everything that's called something value will result in a Neumann value. And the key functionality that we're providing is the knowledge of how to set these Dirichlet and Neumann values up, because they're really complicated to set up. And this is the simplification, or is an interface to generate Dirichlet conditions and Neumann values that
Okay, so let me ask a couple of questions here. So at the mathematical level, before we get to the physical modeling, right? What is the layer? I mean, what we have right now is a bunch of ways to specify boundary conditions, which I have only ever copied examples with them in. But what is the, you know, we got a level which is a pure mathematical level. Then we're going to this level, which is some kind of physics level, right?
That's correct.
What is the intermediate level? Or is that, does there not need to be one for some reason?
For me, that doesn't, it's not obvious.
So what would be, well, how would you write this out? As if I were to just evaluate that.
You'd get Dirichlet conditions.
Okay, hold on, let me just do it. Let me just go ahead and do this in another notebook so I don't mess this up. Oh, that didn't work. Oh, because
you need to copy the rest of it as well.
No, I'm just going to do it here. What? What's going on here?
There's a typo.
Oh. Okay. So that's what this actually is. And by the way, it might be useful to show that in the documentation.
Okay. I've typically done that on the reference pages for the conditions and values, but I can do it here as well.
No, I'm not sure. Okay, all right. So let me understand this. So this is the other way around. This says what the constraint is and then where that constraint occurs. Is that correct?
That's correct.
Okay, so for some reason this has switched it around.
Yes, we've switched it around because when I look at a PDE model and I see the equation and I see the boundary conditions, the first thing I need to know is what type of boundary condition is, and then that's what's in the name, and then where it's applied. The specifics of the exact value are not that important right away, but this is optimized for readability.
Well, so what would parameters be? So parameters, I'm rather confused by this. No, I see that. I see that. That's the parameters that go into the equations, and which ultimately would potentially be part of those boundary conditions.
Correct.
Okay, but so anyway, so the basic scheme, which I'm not totally sold in terms of argument order and so on, but the basic scheme is that whatever this original thing you're currently calling a model, which should be called something different, is that has, so the parameters there, this is vars. That first argument here is vars. Is that correct?
Yes.
Okay. And the second argument is the parameters.
That's correct.
Okay. So, okay, so let's see how we solve this. So if I take, boy, so this could have units. The 343 could have units, correct? This 343 sound speed could be in meters per second, right? You could put units in there, right?
I'll check that.
Well, you have to, you must know, because it's got to have a whole bunch of code to deal with units.
Then it doesn't.
Well, it needs it.
Okay.
Okay, because what people are going to do is they're going to say sound speed goes to, and they're going to say control equals speed of sound, right? Mass density, control equals, you know, density of aluminum, you know, alloy such and such, right? So that absolutely has to work. And that means you've got to be able to untangle in the pre-processing for the PDEs, you've got to be able to untangle the units and reinsert them at the end, right?
Okay.
And I don't know exactly how, but is Rob here? Can you comment on the infrastructure for that?
Well, I think reinserting in the end is going to be
well, then you got to figure out how to do it,
because what I mean, what we're doing is we're setting up models or equations, whatever you want to call them, that set up an equation that you then solve. It's not, you don't have a whole function which is called solve acoustic equation.
I understand. So you solve the equation, and what the equation has units in it, and the result should be an interpolating function either with units or some kind of thing where the units are wrapped around it.
Yeah, but so Stephen, that's a whole nother, I mean, that's a huge project to try and get units injected in ND-solve generally.
Okay, but then I'm afraid this isn't going to work. I mean, because people are going to give this with units. So you've got to figure out, what are you going to do with that? You're going to reduce it to base SI units, or what are you going to do?
Yeah, I think we would reduce it to base SI units.
Okay, and then you give a result, and then how do people interpret that result? Okay, you got to come up with a solution to this, okay? And I suspect the correct solution is, I mean, I think you should examine what is involved in getting units will float through ND-solve, right? They can be stripped at the beginning, the solution is made, they can be inserted at the end.
Yes, right? But that's a significant project to make that work.
I understand. So to figure out what to do. I mean, okay. So, I mean, having this, documenting this as it'll lose the units is a pretty unfortunate thing to do. But, maybe if it's experimental enough, I suppose we can do that. Am I making sense?
I see what you're saying, Stephen, and I think it's correct. We should think about this. I do want to point out that in my opinion, the value of this functionality is actually in the providing of the PDE term operator model, or whatever you want to call it, because those are not easy to set up. And I think
completely agree. And I've been pushing for this for 15 years or something for us to have this.
So
but the thing I think we should do first is Laplace equation before we do all these fancy equations. But anyway, you'll do that.
I also agree with that. We can add them, and I will add them. One thing to keep in mind, though, is that we need to have a certain level of complexity in these things that we model from the physics point of view to be able to say that the approach, the framework we put into place works generally.
Oh, I agree. Okay. But I just don't make the mistake of forgetting the basic things.
I'll do that. I'll add them.
Okay, fine. But so for those things, see, the problem is as soon as you call something sound speed, you're setting up something that needs units.
Okay.
That's the problem. So, if this was called, if it was just parameter X, I'm not saying it should be, one wouldn't expect you to have units. For the Laplace equation, for the Helmholtz equation, I don't expect units. But I do expect units by the time I'm filling in something called sound speed.
If you look at the notes, it is documented, the units there, if you scroll up in the notes.
Okay. Well, fine. But so now I have another question. The physical quantities framework, how does that relate? I mean, presumably you can give entities instead of the string sound speed here. Is that correct?
No.
Well, you need to figure that out. Right? Do you know about the physical quantities framework?
Yes, but the problem with that is that it's somewhat limited. If you want to have material parameter of something very specific, most of the time I just don't find what I need.
Okay, well then make sure it gets put in there because it should be in there.
Okay, I'll
push
the people.
So I mean that's what physical quantities are about. And the whole point is we can analyze, our dimensional analysis system and so on work with those physical quantities. Am I making sense?
Yeah.
So, and for example, you should be able to use that to, de-dimensionalize things if necessary.
Mm-hmm.
But the point is that has to, so, and the canonical names you're using here have to agree with the ones for physical quantities, right? Presumably they do.
They do that.
Good.
That's, to the best of my knowledge, they do that.
Okay, fine. But so then you should support either, in the canonical form here, I think should be an entity there, but you can, for convenience, you can let people enter them as strings. Does that make sense?
Yep.
Okay, so
If you scroll up, Stephen, to just the documentation of the parameters there should be a table at the end for everything. There it is. Yeah.
Okay. All right. Well, that's not going to always work. I mean, I'm sorry. People are going to give temperatures in Fahrenheit, and they're going to do all kind of Fahrenheit differences and so on, all kinds of funky things, right? And I don't really understand.
That was a really bad example. That's one thing we can't do. Temperature, we can't do temperature differences.
Why not?
That's one of the failings of our unit system.
No, we can do temperature differences. We can. I mean, what's tricky is, yeah, anyway, we can do temperature differences. Okay. What happens if I want gravitational waves and I want a quadrupole source?
Then you'll have to model it with several dipole sources.
Okay.
So we have monopole and dipole sources.
I can see that.
Yeah, and then if you want more higher order sources, you'll have to model them yourself. That's the limitation of the model.
That's fine. Okay, let's see here. So, what should I? Okay, so what is something like this? How is that used?
It should say there in the very beginning, typically used for.
I don't think that font is right, but that's a very minor thing. Okay, represents time or frequency domain absorbing boundary condition. Absorbing boundary, acoustic absorbing value.
So since we can't have infinite domains in finite elements, or how do people simulate it? Well, they simulate a finite domain and they have an absorbing boundary value that behaves as the infinite thing. So that's what the text says to you there.
But so this object is going to be something, this is a Neumann value, which, so in other words, what you're saying is in the PDE, this is like, there could be a piece in the PDE that says, you know, y prime of blah, blah, blah equals blah, 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 comma, Neumann value, whatever. Is that right? Is that how we set it up?
Yes, I think that's correct. And if you scroll up to the top, there is an example of how it's used. So it says right at the top first. So there it says acoustic model equal absorbing acoustic absorbing value. So the acoustic model operator, whatever, gives the part of the equation, while the value or the condition gives the boundary conditions.
I don't understand that. I mean, normally aren't the boundary conditions separate? You know, you have in the bulk,
yes,
you know, whatever.
You're correct about that, but we cannot really do that. And the reason is the following. Because the Neumann value does not necessarily depend on the dependent variable. And if it's floating around in the list of equations and boundary conditions, we cannot associate the Neumann value to the part of the PDE. You have to think about coupled PDEs, for example. Then it's not clear which dependent variable a specific Neumann value belongs to. That's why it's part of the equation, so that we can associate a specific Neumann value to a specific part of the equation.
Okay, but in the way that we've set it up, okay, we have the idea here. This is a Dirichlet condition which says this dependent variable at this position. I mean, why? Okay.
Yeah, but
question,
Neumann values are different. They depend on the weak, they come from the weak form of the equation that's actually used to solve. So they depend explicitly on the actual equation that's being used. So it's not just an extra term you add, you put in separately.
In my naive understanding of this, they have a derivative piece, right? They depend on things like fluxes and so on, right?
Correct.
Yes, it's actually an integral condition, basically.
Well, is it a flux condition? Is that what it really is? What is it?
Yes,
I mean, go ahead.
It's a flux condition. So it's basically everything that's behind the divergence. So you have an inactive diff, and then there comes a whole slew of stuff, and all that stuff relates to the Neumann value. And that blah, 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 dot gradient stuff, that is a flux. And what
okay, so in other words, when you've got a div here, the grad inside here is the flux, and that's the thing that you want to set equal to 0.
Yes, and
okay.
that's done in a weak sense. That's what Rob is referring to.
What do you mean by that?
So
like an integral equation. So if you look at Neumann value. Neumann value page, reference page, it's actually explained there.
What did I do wrong here?
Well, probably another n.
2n.
Spell checking should deal with that.
It's a pity.
Somebody should report that. Can we get that? Okay. So,
it's in the details section.
Well, I'm trying to understand this. Equals Neumann value, and then there's a Dirichlet condition, which is over here, and then there's a Neumann value.
Right. And because the Dirichlet condition always has a reference to the dependent variable, we know where it belongs. But the Neumann value is just one there. So if you have u and v as dependent variables in the system of equations, you don't know where to put that Neumann value. And it actually makes sense to make this Neumann value part of the equation.
Yeah, this makes sense.
Because the integrals are related.
I remember when we designed this, yes. This was a painful design process.
Yeah, it was painful. We thought about it for a long time.
I think it's pretty good, actually. This makes a lot of sense.
Yeah.
So in a sense, this is a generalization. Okay, fine. I get it. All right. It's a little bit of a weird name there.
We stuck with trying to make the names consistent, so that if you look at the name and it says something value, you already know this is part of the equation.
Big problem that I have with this is, there's basic mechanics. We don't even have, basic ODE mechanics. We have not physicalized things to talk about basic ODE mechanics, right? Except in the framework, except in our, Lagrange's equations, or God knows what else, right?
And basic system modeler.
Well, I understand, but we don't have that wrapping here, right? Now, maybe that's because, one thing to say is there are a lot more ODEs that make sense to solve than PDEs that one can reasonably solve. That's one argument for that. But one would expect, given that one has, argue through this, okay? Is that a correct reason why we're doing it this way? Because there are only like 5 PDEs that one can solve type thing?
No.
So explain.
I think the big strength, and Oliver can complement, the big strength of the framework that we have for PDE modeling and so on is that it allows you to mix different kinds of physics.
No, I understand that. That's not my question. My question is, if you're looking at the system from the outside, right, I would say, okay, show me a harmonic oscillator. Oh, we don't have those. We have complicated acoustic absorption models, but we don't have a harmonic oscillator. How come?
Yeah, I see what you're saying.
I see what you're saying. We haven't built a modeling layer. To be honest, I think that for that
it's a lot easier. Most people can write down a harmonic oscillator, whereas they can't write down.
And that's why.
But the other thing is that when you model those things of some complexity, you abandon equations, or you have something where, as a modeler, you don't actually explicitly use equations. That's what system modeler, bond graphs, and all of these tools do. They get you a level above equations. Mm-hmm. And equations is it's like the machine language. You eventually compile it to equations.
I understand. But my question is, for purposes of explaining what's going on, and for purposes of having, I don't understand why we don't have harmonic oscillator. By the time we have an acoustic model, we should have a harmonic oscillator, right? Because the harmonic oscillator also has certain parameters. It has a natural frequency, it has a damping, et cetera, which we can understand.
Yeah, but the problem with that same damn problem with the named equations. They don't compose. you can't, they're not the building block. They're sort of a final piece. You know, they might have parameters,
well,
so there's some flexibility, but they don't compose. There's no composability. That's what happened with the ODE modeling frameworks. They built something that has composability. That's what all the, you know, that's what bond graphs do. That's what System Modeler, Modelica does. That's what they all do. There's sort of composability. You can actually build something.
How is this composable?
It's composable in a much narrower sense, in the sense that you get a core model and you get a bunch of boundary conditions. Then you add domain. You can mix the domains. They happily mix. So you can have multi-physics.
So for example, if I have an acoustic model and I also have a diffusion equation running, how do I do that?
A better example might be you want to model fluid dynamics and heat transfer. So you have
we don't have fluid dynamics yet.
No, but it's coming.
But even if we don't have the model right now, the first thing is we can add that, and the second thing is you could still write the model there and use these operators or these terms or whatever to complement them.
I see. And so your point is that the harmonic oscillator kernel is kind of trivial, but these are not trivial.
Yes.
Yes.
Yeah.
But I
and
still
it's the same for the engineering, the ODE style modeling. You know,
but I think that there's as much composability. If we had a harmonic oscillator,
but the minute you make it an equation, you can't. Like
no,
in this case,
I understand. So it shouldn't. Okay, so that's your argument for why these are terms, not equations, which I'm beginning to buy. Right? That's why you don't want to give the thing as boom an equation, but there is still a harmonic oscillator kernel. You know,
sure,
that isn't.
Sure. And you might want to model an array of harmonic oscillators. I mean,
right, which is fine, which you could do if you had them as terms rather than equations, correct?
Exactly.
Mm-hmm. Right. So that is an argument for having Laplace operator, you know, wave equation operator, rather than wave equation. I agree with that.
Yeah, absolutely.
Okay. So now my next question would be, in what sense could this be thought of as an acoustic model operator of some kind?
So you can directly feed this to, I mean, for example, the frequency version, you can directly feed this to ND eigensystem and compute eigenvalues and eigenfrequencies.
No, I understand that. But this thing is, what it is it's a term in an equation.
Yep.
Right? What term is it, really? What is the physics of what this term is?
It's the term of the full dimensional object that you want to model. The boundary conditions are the...
Okay, but what is it physically? I mean, like in the case of, well, I'm trying to get it's not a very good argument because yes, I mean, like if you ask for the Laplace equation, you know, del squared, you know, for electrostatics, for example, del squared phi is just, you know, I don't know what you call that. What do you call that? I mean, del squared is the operator. What's that?
You might call it Laplacian term.
I mean, so the thing, I agree with you. The naming is difficult in that sense because we've used the dependent variable in the equation. The operator would be a function, basically.
I agree, which is not what we want. Although there are plenty of people who will talk about using the heat operator or the heat kernel to mean the kernel, right? And that might be useful in its own right. Just like we have Laplacian, we could as well have heat kernel. See what I'm saying? So you can say Laplacian of F. We could also say heat kernel of F. Does that make some sense?
I'm trying to think.
I mean, it'll have parameters.
Yes, it must have, because otherwise it's yeah.
I think that you're going to have a bunch of placeholders for all the dependent.
Yeah.
I don't know whether that makes sense, but I think in the case of the heat kernel, it probably does make sense. And people use that terminology just like they use Laplacian. I mean, you could say, why do we have a Laplacian? Why not make it from, you know, div grad type thing?
Sure.
Mm-hmm. So this is going a bit in a different direction. This is basic physics operators, basically. I mean, the thing I'm concerned with more is about engineering applications. So it's tangential but slightly different.
Yeah, but I understand. But so, okay, so look,
might be a different or an additional project to do something like that.
Yeah, but we are going to need that because people, I mean, given the framework you've made, the heat kernel and solving, I mean, you know, okay, let's come back to this. Okay. So this thing you call acoustic model, it's a something term. I don't know what term it is, but it's a something term. It's not a model, right? What is the name of the equation that we're dealing with here?
So for the time-dependent part, it's a wave equation, and for the frequency domain, it's a Helmholtz equation, both generalized.
Okay, and are all applications of this referred to as acoustics? I mean, you know, one talks about acoustic modes in who knows what. I mean, in cosmology or things like this. They're still called acoustics, so maybe it's always used. But is there? I mean, my question is the term acoustic, which is a very application-specific term, is that the correct term for this?
I'm not an expert in cosmology, so I don't know.
Well, we need to know the other applications of this and whether it's always called acoustic. I mean, because
sound would be another
no
term.
No, acoustic is better than sound. Acoustic is more general than sound. Acoustic suggests
pressure acoustics, maybe.
What's that?
Pressure acoustics.
I don't think that helps. What is acoustics when it isn't associated with pressure? Well, I mean that's making it more specific. I don't think that's right. I think that okay. In any case. Acoustic sound hard value. Wow, these are really specific. Okay, so
but these are terms used in
I know that.
Yeah, and they are specific, but they're very hard to figure out. So.
Yeah,
right. But you see, the problem is, okay, look, this is where we get into trouble. We are building a peninsula, a tendril, a tentacle here. And the problem is, unless we have the main body of the animal, people won't even find the tentacle.
I mean, so in my opinion, the main body of the animal is fluid mechanics and structural mechanics, and those two are definitely missing. So
but it's more than that. It's dealing with PDE.
Yeah, wait. But this is not maybe for other areas, but for engineering, we definitely need structural mechanics and fluid dynamics, and not harmonic oscillators and things like that. I mean,
I know, but for most of our users, it's wonderful to be able to build this tentacle. We don't have good marketing into this vertical, basically. And that's the problem. We can't really, yes, we can do all this stuff, but it's not clear anybody's even going to notice.
I mean, this is a requested feature from customers, this modeling language for engineering.
I understand.
Why wouldn't they notice?
Well, because I think that we need to make sure that we have the trunk of the tree as well as its branches here. And that involves having, things like Laplace equations and so on, things that
that's not helping that. That's not helping in that market.
I'm not convinced, Stephen.
No, that's just not in that market. No, but heat transfer, mass transport, those are big. Acoustics is probably a little smaller.
Yes, we started with
structural mechanics, fluid dynamics, super big.
Those are very big. Heat transfer and mass transport are huge.
We'll need a separate conversation about this. Let's focus on this design. Okay, so first thing is, so I don't know, acoustic equation term, acoustic.
That's a lot to type.
Could we just call
I don't care about the typing.
Term?
Don't sell me on typing. Go ahead, what?
Could we just call it acoustic model term?
Yeah, we might be able to. It's a little weird. or acoustic term, perhaps. I don't know whether that even makes any sense. What would it do for the other cases? Heat term is not going to, heat transfer term.
Mm-hmm.
See, what is it that, what is the thing that's equal to 0 in these PDEs? What is the name for that?
In my opinion, it's always the model. Everything is put on the left-hand side in that model.
Yeah, but that's a very engineering thinking, and it's not going to work.
Well, I am an engineer.
I understand. Right. So the does heat transfer term make any sense, or does that confuse things? I mean, if we use the term here, diffusion. Well, you're using diffusion term
here. A term is, in my opinion, a term is a single object that you add with plus or something, some other math.
Yes, but that's what you're doing for some of these. Mm-hmm. These things, you're adding it with plus.
But it's multiple terms. So it's, I mean, it's diff, grad, and you have convection operators part of that.
The whole point is you can perfectly well have something here. If you want coupled heat transfer, you would have a sum of multiple ones of these terms, right? Equal to
you have one heat transfer model with multiple variables. You still use only the heat transfer model term, whatever you call it.
What about the right-hand side? The right-hand side has to have its boundary conditions.
Equal to a number of zeros then, or whatever, or boundary.
Or boundary conditions, right?
Yeah.
Okay.
And that actually makes sense for the mass transport model, because you want to have mass transport for multiple species, and it actually works. So you can have multiple species in one mass transport model.
Okay. The term model isn't going to work. We've used it for other things. It's not going to work. So we need to figure out, I mean, and I don't particularly like term either, but what is it? What is the left-hand side? It's not a model. A model is a more general thing. It's the whole ball of wax.
Yeah.
What is this? What is just that left-hand side? What is that called? Do we have, what is the right name for that? I wonder if somebody on our live stream has a suggestion here. Heat transfer components was one thing here, yeah. What is it? What at a physical level, what is the thing? Heat transfer balance or something? What is the, it's something like, it's the thing, but not everything considered is balanced, but heat. Again, let's take electrostatics.
From another point of view, it's everything except the 0 on the right-hand side.
Well, is it always 0 on the right-hand side?
Well, or boundary conditions.
That's the point. It's boundary conditions. So, but what is the thing?
So it's mostly the operator applied to the dependent variable.
I know that, but look, just like you have a bunch of things that you consider to be fluxes, right, that flow through the boundary.
So it's almost always 0, right? Except at the boundary.
Yes.
So
is that always true? Is that always the case?
Yes, I mean, because the right-hand side is also moved to the left-hand side, basically. Yes.
Yeah. I see. So for the Helmholtz equation or something, you move it to the left-hand side.
Yes, you can always move to the left-hand side, and everything is in that left-hand side part.
Okay. So it's the thing other than the boundary.
Yeah.
Bulk term.
So it's always balanced to 0, except at the boundary, where you.
Yes.
Where it sort of interfaces with the environment.
So it's like the bulk. It's the value of. Okay, look, it needs a name. I don't know what the right name is, but I think that's the right. I mean, so essentially what we're doing is the left-hand side of the equation is in the bulk, and the right-hand side is the boundary.
Yep.
Mm-hmm.
Body, boundary, body, bulk.
See, unfortunately, in some cases, it's more like bulk. I mean, it might be free space. I mean, it might be that the interior, interior, but that's not necessarily correct either, because the boundary conditions could be wherever, right?
That's true.
Yeah.
But it's,
interior, exterior is not totally terrible, but let's take a look at what the structure of these things is supposed to be. So you're saying that, but by the way, I mean, I assume that we can do, once you've specified the equations, we can do kind of industrial scale
yes, and we've written
versions
a
of
whole
this.
yes, and we've written a whole set of monographs about just that.
Wonderful.
Yes. Really a large scale, and from papers and stuff like, oh, this is another question for you, Stephen. So I have people that have used NDSolve and PDEs and stuff to write papers and whatnot. How can I make those notebooks and stuff like that available, easily available from within our documentation?
I'll have it in the notebook archive and link to it, I would think.
No, well, I mean, no. I think in the 21st century, we should have something like an automatic installer or something like that, not linking. So could we have, for example, a guide page advertising that, saying this is a repository of externally contributed PDE models or something like that? Here's how you install it, one line.
Well, I think that's what our repositories do. That's what we should do there. Are you saying that, wait a minute, are you saying that people have created things which are specialized, you know, for solving the heat transfer in a starfish or something? Is that the type of thing you're talking about?
No, so there's several people have used this to make their own models or application examples they've written papers about, and some of them have contributed this to our repository, or one of the repositories on GitHub. So for example, somebody did a bell acoustic, so they analyzed the harmonics of a bell.
Okay, but the bottom line is they have made a model that is based on our building blocks, but is a more sophisticated model. Is that the idea?
It's not based on these building blocks. They're not
well,
published yet.
I understand that, but it could be based on these building blocks. Conceptually, it's based on these building blocks.
Yes, correct.
Okay, so that's exactly what our repositories are for, and that's the right way to handle this. For example, look at the neural net repository, right? It is exactly the same kind of thing. It is specific. You know, if you look at the neural net repository, and by the way, I'm going to have to go in a few minutes here. If you look at the neural net repository,
I'll have a look, yeah. Sure.
Here, but I mean, let's just look at one. I mean, this is a particular, right? So this is a particular model that uses our building blocks here, right? But this is a particular model that is a particular
How
thing.
do you install that? How do you get that?
You just say it like this. You go, watch, it's beautiful. Da-dun, da-dun, ba-bum, ba-bum. Okay, well, this is because we have the wrong version. But I mean,
but
just works.
Okay, right. But we don't have like a PDE model kind of container. So
I know. So I'm saying we have to create something like that.
Okay. Yeah.
Right. And then this is the right way to do it. So then the documentation is on the web, and
there is no documentation in product for this.
Nope, absolutely not.
Stephen, come on.
There will not be, and there will not be, because we're moving all of our documentation to the web.
I mean, it would be nice if people could just look at it in the way they're accustomed to.
That's what they will be able to do. That's what our repositories do. We have a whole framework for this. That's how it works beautifully. Nobody has a problem with it. And there's the result. Okay, so that's what we would do here. Right? This is literally a request I have never heard, is a locally cached version of the repositories. I mean, it also happens to be crazy because the repositories are huge. I mean, we have a good framework for this, and that's what you should use. I mean, you know, the neural net repository, the function repository. And by the way, you can put some preliminary things, and users can put things in the function repository. Right? This is the right way to do it. And okay. So, I mean, we're going to have to wrap this meeting, but.
So we're going to have to continue, right, Stephen?
Yes, we will have to continue. This is a good introduction, and it's very impressive what you guys have done. I'm just getting used to the fact that
I know it's good. It's a good process.
Right, but I'm going to insist that you have the more elementary things here. I don't want the same mistake that we made with, you know, regions and no triangles type thing.
We had lots of triangles, by the way.
Now we do. Now we have lots
No,
of triangles.
no. We really did from the get-go from regions. We had lots of triangles.
I understand you had lots of triangles, but you didn't have a way to specify them.
No, we did. You insisted on these high school triangles.
Okay, so I'm insisting on college.
And we built
PDE.
high school triangles.
Right.
Yeah. College physics operators, which is fine.
Yes.
So
it's fine.
how is the repository different? Somebody's asking for a wiki of notebooks. It's very different because the repository has all of the plumbing to just be able to use the thing directly in the session. And it gets cached once it's, I mean, for things that are big, this network is now cached on this machine. Bob on our live stream is saying flux operator, I guess in reference to what the name of the thing that is the left-hand side. But I don't think that's quite right, is it?
There's more than, the flux is just one part of it. You can specify stuff outside of the flux. Yes, so
Yeah.
it's more than flux.
What is it? Gosh, that's crazy that there's no
To the
obvious...
best of my knowledge, there is no name for that.
Well, so we ought to make one up.
Go ahead, yeah, sure.
That people can understand. I mean, it's, you know, it's something like
acoustic interior.
Yeah.
I mean, the thing what we're doing is we're
Heat
relating
interior.
the full dimensional model to the boundary, and that's
Yeah, right.
bulk to boundary basically.
Yes. Acoustic bulk term.
Well, sounds a bit bulky, doesn't it?
You don't like it? I mean, but what is the... Again, I'm coming back to acoustic term.
Yeah, I don't think.
Probably,
I don't think term is terrible.
It's too bad. Yeah. I mean,
you've got diffusion term here, and you can have a
we've used that for the basic operators, for the generic operators.
I mean, and a term doesn't have to be just a single term. It can be, you know, multiple terms together.
Right. So you could have diffusion term, and what you're saying here is you say diffusion term of blah 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 plus conservative convection term equals right hand side.
Yeah. So that's basically it's a concatenation in some way of specific generic terms. It's like a higher level, a next level.
No, I understand, but I think it could be a term as well.
Yeah, I think it's not terrible because people will at least then understand that that's something that's not an equation itself. It's something that goes into an equation.
Exactly. That's what we're saying.
I see what you're saying, Stephen.
And then that thing where it says, yes?
I mean,
heat transfer term, blah, 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 equals heat flux value. It's not terrible.
Yeah, maybe. I'm just concerned a bit that people are looking for PDE models. You know, so we need to
that's why we're going to have a PDE model repository, and they'll know we have lots of PDE models. I mean, that's a question of documentation and keywords and so on. It's not going to be a problem. It's more important that people can read the thing we have. You know, acoustic term blah 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 equals acoustic absorbing value. Can it end up with acoustic absorbing value plus acoustic impedance value?
Yes, yes, sure. Work? You can add multiple boundary conditions. I mean, they can be on different parts of the boundary, so you'd need to be able to add them.
I see. And
you can even have multiple boundary conditions at the same spot in some cases.
Right. So, okay, I need to go to a different live stream, which I encourage people who've been watching this. We are doing a live stream about code assistance, which will start in a moment here. Yeah, this is very interesting. Okay. I mean, just trying to think what else we need to talk about immediately here. The structure of your thing with that initial. Would you not also want to give some association form of the first argument that says dependent variable, arrow, blah, 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 and so on, rather than the list? Do you already have that?
That's I think not a bad idea. What would be the benefit of it?
It's useful for documentation. If somebody wants to see exactly how it works, they're seeing it in a textbook and they just see dependent variable arrow t, independent variable arrow t, and so on, they immediately know what they are. They don't have to look up documentation. I think we should support it. I think some people will use it, some people will not. People who are just typing it in won't use it, but if they, if this is their master equation and they're going to say it only once, they'll probably put it in that more elaborate form, because it's more important that people can read it than that people, if you think about it in a paper, it's a wonderful self-documenting thing. You don't have to say where blah, blah, blah is blah, 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 blah. Anyway, I have to go to this other meeting, but impressive. Okay, to be continued.